The mechanism for the Williamson ether synthesis starts with the formation of the alkoxide that we need to do the substitution reaction. So this is the overall Williamson ether synthesis, and it starts with an alcohol. And then the alcohol has a proton removed in step 1 with sodium metal, potassium metal, sodium hydride, a variety of possibilities there. So we need a strong base. And then, and I'm just going to list potassium, NaH, NaNH2, etc. And then the alkoxide will displace the leaving group in step 2 to give us our ether. So let's start with our mechanism. First of all, the electrons, there's one electron on sodium that can pair up with an electron that comes from the bond with hydrogen, and then an electron will go off with hydrogen. So a funny little reaction that gives us our alkoxide and then an H dot. That will pair up with another H dot to give us our hydrogen, which bubbles off. So we form our, in this case, a sodium alkoxide. Then we'll use that in our next step. So the sodium alkoxide, the anion, will add to the carbon and displace the leaving group. So that's an SN2 reaction. And in that we get our ether. So that would be the Williamson ether synthesis. So the reaction that I've drawn down here just reiterates that we could use a number of different bases to do this kind of reaction. So in this case, it would be this sodium hydride. This is essentially an H minus Na plus, and so the H minus will add to the hydrogen and leave the electrons. That leaves hydrogen gas that will be evolved, and there's our sodium alkoxide again. So a number of other bases that we can do this reaction with, including the metals, the hydrides, and so forth.